Have you ever wondered how your social media feed knows who your friends are, or how your music app can build the perfect playlist? Well, it all comes down to a secret language that organizes our world, and today, we're going to decode it. This is set theory, and it's the hidden logic behind pretty much everything. So let's dive in. First up, we're going to start with the absolute basics, the main building block, the set. Then, we'll see what happens when these sets start to interact with each other. From there, we'll learn how to build relations, which are just the rules that connect things. And finally, we'll dig into the really cool properties that define those connections. You know, we group things together all the time without even thinking about it, right? A playlist of your favorite songs, a grocery list, a specific box of tools in your garage. These are all just collections of stuff. But for math to do its magic, we need a really precise way to talk about that idea of a collection. And in math, that word is a set. Now, a set is simply a collection where every single item, we call them elements, is unique and clearly defined. There's no maybe, no kinda, sorta. An element is either in the set or it's not. And that simple black and white clarity, that's its superpower. So instead of having to list out every single member of a set, which could take forever, we can just write a rule. This is called set builder notation. And you can think of it like a bouncer at a really exclusive club. This rule for set A here basically says, all right, you can get in if you're an integer, that's what the Z means, and you have to be strictly between 2 and 7. It's a clear, simple rule for membership. And here they are. These are the ones that made it past the bouncer. This is what we call roster notation, which is really just a fancy way of saying a list of the members. The integers that are bigger than 2 but smaller than 7, well, that's just 3, 4, 5, and 6. See? 2 different ways to talk about the exact same group. Okay, so we know what a set is, we know how to describe one with a rule or a list, but what about one of its most basic properties? I mean, how big is it? How many things are actually in it? This number, 26, is what mathematicians call the cardinality of the set of letters in the English alphabet. Cardinality sounds complicated, but it's not. It's just the official term for the size of a set. Literally just counting how many unique elements are inside. Now this leads to a really fascinating question. If you start with a set of things, how many different combinations or smaller groups can you possibly make from them? Think about it. If you have 3 toppings for a pizza, how many different pizzas can you make? The set of all those possible combinations has a special name. It's called the power set. So if our original little set is just A, B, C, its power set includes every single possible team you could form. You can have a team with nobody. That's the empty set. You can have each one by itself. You can have every possible pair. And of course, you can have the original team of all 3. This idea of finding all possible combinations is absolutely essential in fields like computer science and probability. So we've got a good handle on what sets are, but they don't really become useful until they start interacting with each other. So let's check out the basic actions we can perform with these sets. Let's go back to our music analogy. Imagine you and a friend are comparing music libraries. A union is like merging them. You get every single song from your library and their library all thrown together into one giant playlist with no duplicates. An intersection, on the other hand, is much more exclusive. It's only the songs that you both have. It's your shared musical taste. All right, let's make this crystal clear with some numbers. We've got set A and set B. Their union? You just dump them all together. You get 0, 1, 2, 3, 4, 5, 6. Simple. Their intersection? Well, you look for what they have in common. The only number in both sets is 3. And then there's the difference, A minus B. For this, you start with everything in A, and then you just kick out anything that's also in B. In this case, we kick out the 3, and we're left with 1, 2, 4, 5. Okay, we've totally mastered individual sets and how they can be combined, but now we're going to level up. What if we want to define a very specific relationship between elements? We're about to go from simple collections to structured connections. So a relation is more than just a group of items. It's a set of ordered pairs. And trust me, that word ordered is everything. It's the key. An ordered pair, like A, B, is not the same thing as B, A. It creates a specific one-way link from the first element to the second, all based on some rule we define. Let's look at an example to see how this works. Imagine we've got 2 sets of numbers, and our rule is super simple. An element A from the first set is related to an element B from the second only if A plus B equals 3. That rule acts like a filter. So 0, 3 makes the cut, because 0 plus 3 is 3. 1, 2 also works, but a pair like 1, 3 gets rejected because 1 plus 3 is 4, not 3. The relation is only the pairs that follow our rule. So we can create a relationship with a rule, but we can go even deeper. We can actually start to classify these relationships based on the properties they have. This lets us understand the basic, fundamental nature of the connection itself. To do this, we're going to run a little diagnostic. We're going to check for 3 key properties. Is the relation reflexive? Is it symmetric? And is it transitive? Think of it as a simple 3-point checklist for figuring out what kind of relationship you're dealing with. First up on our checklist, reflexive. This is the easiest one. It just asks, does every single element in the set relate to itself? So a rule like is equal to is reflexive, right? Because 5 is always equal to 5. But a rule like is greater than is not reflexive, because 5 is never greater than itself. Next up, symmetric. Is the relationship a two-way street? If A is related to B, does that automatically mean B has to be related to A? The rule x plus y equals 15 is a perfect two-way street. If 10 and 5 are related, then 5 and 10 are too. But is greater than? That's a one-way street. If 10 is related to 5, 5 is definitely not related back to 10. And the last item on our checklist is transitive. Think of this like a logical chain reaction or the friend of a friend property. If A is related to B and B is related to C, does it follow that A must be related to C? The rule is taller than is transitive. If Alice is taller than Bob and Bob is taller than Charlie, you know for sure that Alice is taller than Charlie. The connection just carries right through. So you might be thinking, okay, that's kind of neat math, but so what? Well, this is the invisible architecture running our digital world. Relational databases, the things that store almost all the world's information, are built on this. A social network is just a giant set of people with a is friends with relation, which we now know is a symmetric relation. This is the fundamental logic that makes modern technology possible. And that brings us to a final, interesting thought. We've just walked through the clean, perfect, logical rules of mathematical relationships. But what about human relationships? Think about the relation trusts. Is that transitive? If you trust your best friend and your best friend trusts some stranger, does that automatically mean you trust that stranger? Probably not. And applying this kind of logical framework to our messy, real-world connections, well, that shows you just how complex and fascinating things can really be.